What's good, my pre-calc party people? It's me, Miss P, coming at you today with section 7.4. 7.4 is a doozy, not gonna lie. 7.4 covers the double angle, half angle, and product to sum and sum to product identities, which is a lot. So we're gonna chop it up a little bit. That's me chopping on my desk here. We're gonna chop it up a little bit, make it a little bit more tangible, a little bit more digestible, focus on one thing at a time while we out here doing our distance learning during COVID-19. So today we're going to focus on double angle identities today. So you'll notice that this says part 1, double angle identities, and that is what we are about to do. So let's get it popping and get to it. Make this a relatively short video considering all my other ones are like 45 minutes or so. Oh yeah, I forgot. This is a little image from the web of the double angle identity for sine and cosine. It's just like a little bit of a visual proof for it. I'm actually going to link a Wolfram Alpha link that has like a visual representation of the proof for sine. Just in case you were wanting a little bit of a visual aid to your mathematical time. And the learning objectives for this entire section 7.4 in our book, is students will be able to derive and use the double angle identities for cosine, tangent, and sine. Students will be able to develop and use the power reduction and half angle identities, which is coming soon. Students will be able to derive and use the product to sum and sum to product identities, again, coming soon. And lastly, students will be able to solve applications using identities. So today we're specifically going to zone in on deriving and using double angle identities for cosine, tangent, and sine. It kind of falls right into applications using the identities. I don't know why I didn't circle that as well. This is kind of like sprinkled in throughout. But today we're specifically talking about double angle identities, and we're going to develop them for sine, cosine, and tangent. Actually, your warm-up, I linked a wonderful video from a professor of deriving the double angle identities for cosine, tangent, and sine. So you've technically already hit that guy off the bat. Now we just have to actually be able to use those identities. So let's get right to it, shall we? So what's the point? What's the big deal? What's going on here? The big idea essentially is that we're talking about equivalence. We've been talking about equivalence forever, it feels like. But that's what makes trig identities and trig subs difficult, because there's so many different equivalency ideas going on. But the essential understanding is that these double angle identities are special cases of the angle sum. So in the last section 7.3, we talked about sum and difference identities for sine and cosine and tangent. These are just special cases of the angle sum identities, as seen when the derivation warm-up problem came up, right? So we know that we can develop these from the sum identity for cosine and vice versa, and make a bunch of manipulations and end up with these double angle identities. Double angle identities can be used to find exact trig values for certain angle measures. That's the big deal, right? Like, the reason we want to do this is because we need to find exact trig values without using a calculator for certain angle measures. Now, the reason that they're called double angle identities is because you can use double angle formulas to find trig functions for twice a given angle. It doesn't have the word double for nothing, right? So they use the word double angle. So for twice an angle, right? The double angle, 2 times any angle is what we're going to be using this for. And you will see that we're kind of working backwards on the last example I have today, but for your homework, I'm linking another of that professor lady's really good video. It's about 18 to 20 minutes or so of her going through using more double angle identities to be able to see how, like, given just one angle, how can you find twice a given angle? How can you find sine of 2 theta? And vice versa, the backwards. Given twice a given angle, how can you find cosine of theta? And so on and so forth. But the main idea is we can use these formulas to find trig functions, to find exact trig values for twice a given angle for any certain angle measures. So let's hop into it. All right, in your warm-up, there were the double angle identities that were derived. Again, there are 3 for cosine, 1, 2, 3, only 1 for sine and 1 for tangent. So something that you guys might want to keep in mind throughout this entire chapter is cosine's been very special in that the cosine sum and difference identities were a little bit different than normal, and similarly for double angle identities, cosine has 3. So I don't really know anything else to tell you other than cosine has a lot going on. But from that warm-up video, we found and derived that the double angle identities are as follows. Ready for some movie magic? That's supposed to be my sound effects. So the first double angle identity is that cosine of 2a equals cosine squared a minus sine squared a. Also, cosine of 2a is 1 minus 2 sine squared a. And lastly, cosine 2a equals 2 times cosine squared a minus 1. And then also sine of 2a is 2 sine a cosine a, tangent of 2a is 2 tan a divided by 1 minus tangent squared a. And now in that video, she used the letters a, or like a and b for different angles. We tend to use alpha and beta. So in our textbook, in case you like having the alphas and betas and not a's and b's or whatever, I decided to provide this as well. Again, here's our cosine 2a is cosine squared minus sine squared. 1 minus 2 sine squared, 2 cosine squared a minus 1. Have them all provided here for you in case you like working with alphas, because the examples I'll be doing today are with alpha. I believe in your textbook, alpha and beta are typically used, but I mean, it's really just a variable, so it's no big deal. They're just representing a particular angle. Now, it's very, very important that you write this down. You're going to need all of these double angle identities today while we're working through the problems. Also for your homework, it's going to be really important as we work through the rest of this unit. You're probably just going to have, honestly, a single piece of paper filled up with all of the different trig identities that we have, and you'll see why equivalency is such a big idea, right? So write that down, Patrick, write that down. Take a moment, pause this video, write these double angle identities down. You can choose the top picture or the bottom. It doesn't really matter to me. You must write this stuff down. And then a tip that I really should look up her name. The professor had said in one of her videos is that she encourages her students to write down the identities at least 2 to 3 times a day. And had gotten feedback from her students that really helped. I would recommend that too. So write this down. Okay, let's put the formulas to use, shall we? I want to make this a shorter video than all of my other ones. So I want to get to the 3 examples that we're going to do on double angle identities today. I think you guys are going to like them. They're a lot more applied than you might think. I know you guys are not vibing with the proofs, but they do get easier over time, I promise. So it's time to put in the work. Yeah. Okay, I'm done being extra. So our first example that you might encounter while working with double angle identities would be to use a double angle identity to find function value. So this is the first example. So we're going to use that identity to find a specific function value. So here's our problem. Given sine of alpha is the ratio 5/8, find the exact value of cosine to alpha. So we're given a very specific value right here for sine. SOHCAHTOA, however you want to think about this. Sine of some angle is opposite over hypotenuse. 5/8, that ratio. We need to find the exact value of cosine of 2 times that angle. So sine of one angle is 5/8. What is cosine of double that angle is what we're really asking here. So let's jump into it, shall we? I'm going to throw up the double angle identities here just because we're going to reference them. And to start off our solution, we're going to have to use the double angle identity for cosine in terms of sine. So using the double angle identity for cosine in terms of sine, and looking at all of these, right? These are double identities for cosine, 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 double, double, double. Which one is in terms of just sine. This is cosine and sine. This one's 1 minus 2 sine squared, and this one's cosine. So we're actually going to use this bad boy, right? Because notice that I'm given sine here, and I want cosine of 2 times alpha. So I need cosine, but in terms of sine. I'm working kind of like from here to here. That's supposed to be an arrow. So we have to use the double angle identity for cosine in terms of sine. So we find that cosine of 2 alpha equals 1 minus 2 sine squared alpha. I just rewrote that double angle formula in terms of sine. I use that double angle identity, the one we boxed. Now, what do we know? We got cosine 2 alpha equals 1 minus sine squared alpha. And I know that sine of alpha is 5/8. So sine squared alpha is just going to be sine of alpha squared, right? This really means, I guess I should have written sine of alpha quantity, squared. That's the same thing. And I know sine of alpha is 5/8. So I'm just going to substitute in 5/8 for sine of alpha. So I have 1 minus 2 times 5/8 quantity squared, substituting in 5/8 for sine of alpha, which was given. Now I just need to perform some arithmetic, right? I need to actually do 2 times 5/8 quantity squared. So if I do that, 2 times 5/8 quantity squared, I get 25/32, right? Note that 2 times 5/8 quantity squared is 25/32. So I'm literally just substituting and doing the math. Now, in order to be able to perform this subtraction, I have a whole number minus a rational number. I need to have them with a common denominator. So 32/32 minus 25/32, getting a common denominator of 32. And bada bing, bada boom, 32 minus 25 is 7, dudes. So we get 7/32 is the answer of cosine of 2 alpha, right? The exact value of cosine of 2 alpha is 7/32. So if sine of alpha is 5/8, then cosine of 2 times that same angle measure is 7/32. Something I want you guys to notice, pause, take a second to think about, right? I brought this up to you guys before. Notice that we started out with sine of alpha equaling a number. Sine of alpha equaled a number, right? So cosine of 2 times that angle is also going to be a number. That's a good sign. If you started off with a number and you use it, you should hopefully end up with a solution that also has a number. Hopefully that makes a little bit of intuitive sense. So just something to kind of help you rationalize your thinking, maybe reaffirm your thoughts while you're working through these. If you started with a number and end with a number, that's probably a good sign. So we are out here. We are working hard. Let's continue with another example. So this one was just using double angle identity to find a specific function value. I found my specific function value is 7/32. Now, a second example that we might encounter is you verifying a multiple angle identity. Now, I know you guys aren't going to like this because it's verifying identities. You guys don't like identity proofs, but I promise it's not that bad. So, and I think I assigned you one homework problem like this. So it's just thinking about those equivalencies again, thinking about how I can rewrite something in terms of something I already know, something I've already established to prove the left-hand side equals the right or the right-hand side equals the left, right? So our objective on this problem is to verify that cosine of 3 theta is equal to 4 cosine cubed theta minus 3 cosine theta is an identity. Once I have it proved, then I can use it, right? So I want to verify that this is true. And this looks totally different. Like this isn't a double angle, this is a triple angle. Like what? We haven't talked about a triple angle at all. What? What? Like, look, this doesn't match cosine of 3 theta. I've got cosine of 2's. I don't have cosine of 3 yet. But we have some previous tools that can help us use one of these and something else that we have already. So, like I said, it's not terrible. I want to show it to you guys. I gave you one problem like this, I'm pretty sure, of verifying something's an identity. And this is kind of like wrapping up 7.3 and 7.4 together as one. So the solution is going to be to use the sum identity for cosine, with alpha being 2 theta and beta being theta, because 2 theta plus another theta is 3 theta. So I'm kind of rewriting this stuff in terms that I'm able to. Let's use orange, why not? Okay, so I want to use the sum identity for cosine, where alpha is 2 theta and beta is theta. Remember, the sum identity for cosine came up last section. Cosine of alpha plus beta, that's this, is cosine alpha cosine beta minus sine alpha sine beta. And now we're going to say that alpha plus beta is 2 theta. 2 theta plus another theta, because that equals 3 theta. So, and we want this expression in terms of cosine only, because check it out, the right-hand side over here is in terms of only cosine. So let's start it off, right? Cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. I'm just starting with the cosine sum identity, right? So that's a sum identity for cosine. And I'm going to say that alpha is 2 theta and beta is regular theta, because 2 theta times plus theta is going to give me 3 theta, right? So I'm just rewriting in alpha is 2 theta, beta is theta. Alpha is 2 theta, beta is theta. And just substituting in 2 theta for alpha and theta for beta, because I have cosine of 3 alpha. Left-hand side is cosine of 3 alpha, which is where I want to start and get my proof going. So something tricky that's going to happen is on the right-hand side. Cosine of 2 theta times cosine theta minus sine 2 theta sine theta is going to start bringing in our double angle identities. Now, cosine 2 theta, we're going to use this one. 2 cosine squared theta minus 1, because remember, we wanted them in terms of cosine only. This is cosine and sine, this is sine. I wanted in terms of cosine only. And additionally, sine of 2 theta, we only have 1 there. It's 2 sine theta cosine theta. So we're going to substitute in cosine of 2 theta and sine of 2 theta in the next line. So cosine 3 theta equals double angle identity, cosine minus double angle identity, sine. Hopefully you're with me still. You're following, you're picking up what we're putting down here. And that wasn't too much of a stretch. Now, let's just work on the right-hand side. I've got the left-hand side with what I need, cosine of 3 theta, right? This guy is good, so let's only manipulate the right-hand side and hope we get 4 cosine cubed theta minus 3 cosine theta. That's what our goal, that's what we want to get to. That's our end goal here. So let's just work with the right-hand side. The left side's good. Right-hand side, I've got 2 cosine squared theta minus 1 times cosine theta and minus 2 cosine theta 2 sine theta cosine theta times sine theta. We're going to have to do some multiplication, some distributions here. So 2 cosine squared theta, 2 cosine squared theta times cosine is 2 cosine cubed theta. Minus 1 times cosine theta is where we get our minus cosine from. Negative 2 sine theta times sine theta is sine squared theta. That cosine theta just remains cosine. So we just did the distribution. All we did was multiply and distribute. And now you'll see that that sine squared is highlighted in pink, because I need everything in terms of cosine again, right? Cosine, 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 sine. I don't want that, but I do know a Pythagorean identity for sine squared. Sine squared plus cosine squared is 1. Solving for sine squared, I end up getting sine squared is equal to 1 minus cosine squared. So just substituting in that Pythagorean identity, I get everything in terms of cosine only. then I got to do my distribution on this little piece right here needs to be distributed across. So I still have 2 cosine cubed theta minus cosine theta. And then this times 1 is minus 2 cosine theta. Negative times a negative becomes positive 2 cosine cubed theta. All that is was just multiplying or distributing that negative 2 cosine theta. Now I got, check this out. I got, maybe I should choose a different color. 2 cosine cubed theta plus 2 cosine cubed theta. That is going to give me my 4 cosine cubed theta. Sick. And even further, minus 1 cosine theta minus 2 cosine theta, that's like minus x minus 2x. You would say in algebra that would be equal to negative 3x, right? That's going to give me minus 3, and my x is cosine theta. So simplifying these, I get 4 cosine cubed theta minus 3 cosine theta. Let me use my colors, which is exactly what I wanted to show was an identity, just by simplifying. All right, like I said, this one was a little bit more complex, but it's kind of fun. It's kind of nice seeing all these manipulations. And I think keeping in mind our goal for the problem and what we want to do, like the fact that we wanted to write it in terms of cosine only because our result had cosine only was really important when making these equivalencies and these manipulations and then working through the algebra a little bit. So that's true. We did it. It wasn't too bad. They're hopefully getting a little bit easier. Now I'm going to hit you with one final example. And that's all I'm doing for today. You guys have another video to watch by the super awesome professor lady. And then you'll be working through some homework problems for me, very similar to these. But I just want to get through it. So example 3, this is the third type of problem you might encounter when working with double angle formulas, double angle identities. So using it to find exact values again. This actually isn't even that crazy. So the exact value just looks a little different than it was before. So our goal in this problem is to find the exact value of sine 22.5 and cosine of 22.5. Now, thinking about these definitely are not angles we know on the unit circle. There's no way you could find sine of 22.5 without using a calculator up until this point. Like you just simply don't know what 22.5 is going to give you unless you used a calculator, right? Yeah, I don't know what 22.5 is other than the fact that it's half of 45. And 45 degrees is an angle we know. So remember how I said that double angle formulas are 2 times an angle, double that angle, right? I can kind of work backwards with my double angle formulas as well. So if I know 45 degrees, I can cut it in half using my double angle to get 22.5. You'll see. All right, so I'm keeping the double angle identities over here. Our goal is to find out exactly 22.5 of sine and cosine. So, solution. The products of sines and cosines having the same arguments, right, where it's 22.5 and 22.5. This is what I mean by having the same arguments, hints at the double angle identity for sine. Because we have sine alpha, cosine alpha, sine alpha, cosine alpha. This is cosine and sine, just sine, just cosine. And then this is tangent. So that means I'm going to use the double angle identity for sine. So out of all of these identities, we're going to use this bad boy right now. Does that make sense? Pause, think for a second. Is that cool? Are you cool with it? If we were in class, I'd ask you guys to give me a thumbs up if you're all right. Okay, so I'm going to use the double angle identity for sine to figure out sine of 22.5, cosine of 22.5. So this is using that same formula, sine of 2 alpha equals 2 sine alpha cosine alpha. If I divide both sides by 2, I'm going to get this. Sine of 2 alpha divided by 2. Note, these 2's do not cancel out. This is 2 times an angle not factored out 2. In that video, she says you cannot factor out a 2. That would not be true. Sine of 2 alpha over 2 equals sine alpha cosine alpha. Like, I literally just did this. Divide by 2, can't factor that out. Divide by 2, these guys cancel. We get this following. So I started with my double angle, and whatever I did on the left, I did on the right. This is not an illegal move. I'm able to do this. I get sine squared alpha over 2 equals sine alpha cosine alpha. Now for this problem, I'm going to switch it. I'm at sine alpha cosine alpha. So sine alpha cosine alpha equals sine of 2 alpha over 2. Sine alpha cosine alpha sine 2 alpha over 2. I literally just rewrote it with sine alpha cosine alpha on the left. And then working here, now I have sine alpha cosine alpha sine alpha sine of 2 alpha over 2. This is where I want to work with. And right now I have a specific alpha that I know how to work with. So we're going to plug in 22.5, considering that's the goal of our problem. Find sine 22.5 times cosine 22.5. I realized I made a typo, so this should be, where is my thing? I realized I made a typo, gosh darn it. So if I wanted to use this, that should not be a comma, they should be multiplied. Multiplied. So I have sine of 22.5 times cosine of 22.5 on the left, so that means my alpha is going to have to be 22.5, and this is sine of 2 times that angle measure 22.5 over 2. So notice that I'm doing this special bracketing because this is 2 times an angle. So I need to perform 2 times that angle. And the reason why I wanted to do that is because it's special, right? So working with the right-hand side only, 2 times 22.5 is 45 degrees. And I just so happen to know 45 degrees. So usually when we're working through these problems, we end up with an angle that we know, something we can evaluate and something we can plug in. So that's a hint. If you're working through one of these problems and you do not come up with a value that you know how to plug in, so most of the times it's just straight from our unit circle. So that's going to be 30, 45, 60, and 90 degrees, or any derivation of those in a different quadrant. You might have went astray. So right-hand side only, sine of 45 degrees over 2 is just by multiplying 2 times 22.5, but we know sine of 45 degrees, that's rad 2 over 2. So plugging that in, substituting in sine of 45 degrees, and then canceling out our double-decker fraction, flipping it, gives us rad 2 over 4 as our final solution. This is our final guy. And that wasn't too bad, except for my typo. I apologize. Exactly. So, oh, you can see where I was trying to write with my white pen. Yeah, so that wasn't too bad. So now, tag, you're it. Here is your homework number 9. Again, I'm going to post that lady's video in the HyperDoc, which are very similar to these types of problems that you guys are going to have in your homework. I find that maybe having an alternate perspective might be helpful. I assigned you 10 problems of only double angles. You're only focusing on double angles, and those are due this Sunday. Alrighty, I will catch you guys in the next video. I hope you have an absolutely wonderful day. You guys are hanging in there. I'm pretty sure this week is AP testing. If you're taking any AP tests, I hope that you guys do awesome. You don't have any technology crashes. You totally own this AP test, and that you have a wonderful rest of your day. Bye!